Hello, my name is Mohammed Sohail, currently studying Mechanical Engineering 7th semester in the National Institute of Engineering, Mysore. The project is International Standard Atmosphere. So, in this project, we are going to model the International Standard Atmosphere, which will be going to helpful for the aeroplane simulation or anything where we can use the atmosphere. So, um, what we are going, this is a small graph which will show the atmosphere, troposphere, tropopause, and mesosphere, and so on. So this is the variation of temperature and pressure along with the altitude. So this is what we are going to model in Simulink. So these are the international standard of atmosphere in a sea level. So when the altitude was 0, the pressure will be uh, 101325.0 Pascal, and the density is 1.225 kg per meter cube, and the gravity is 9.80665 meter per second square. And also the universal gas constant R is 287 joules per kilo kg, and the heat capacity gamma Cv by Cv, which is 1.4, and the sound speed, which we can calculate by the A naught with the formula root over gamma R into T naught, which is 340.3 meter per second at the sea level, and the perfect gas equation where we can calculate the pressure with the help of density and universal gas constant and the temperature. So these all are the parameters at the sea level regarding standard atmosphere. So as we are doing our model project based on only for the simulations for the aircrafts or aeroplanes, so which will be flying below 18 kilometers of the altitude. So we are only interested below the 18 kilometers of our atmosphere, so that we will see how the temperature will be varied below the altitude of 18 kilometer. As we can see, according to the international standard atmosphere, the temperature first starts to decline as we go up, or as we increase the elevation of the sea level, and after 11 kilometers it's going to be constant for until 20 kilometers, and again it's going to increase, and again it's going to increase, and at last it's going to decrease. So we are not interested in this part, we are only interested in this part which is below the 18 kilometers. So our model for the temperature will become from here to here, which is T1 is equals to T naught plus K into H, which is T naught is a sea level temperature, and the K is a constant whose value is minus 0.0065 Kelvin per meter, and the H is a respective altitude at which we are going to calculate the temperature. So this is the temperature model until here, and it's going to be constant until from 11 to kilometer of 18 kilometers. Then this is the pressure and the density standard atmospheric model. So the pressure here will be, this is the model of the pressure from here to here, from sea level to 11 kilometers of altitude, and from 11 to 18, this is what, and again it's going to increase, and again it's going to increase, and at last it's going to decrease. So we are not interested in this part, we are only interested in this part which is below the 18 kilometers. So our model for the temperature will become from here to here, which is T1 is equals to T naught plus K into H, which is T naught is a sea level temperature, and the K is a constant whose value is minus 0.0065 Kelvin per meter, and the H is a respective altitude at which we are going to calculate the temperature. So this is the temperature model until here, and it's going to be constant until from 11 to kilometer of 18 kilometers. Then this is the pressure and the density standard atmospheric model. So the pressure here will be, this is the model of the pressure from here to here, from sea level to 11 kilometers of altitude, and from 11 to 18, this is what it going to be the pressure. And according to the international standard atmosphere, so in here, in aircrafts, the indicated aircraft velocity and the true aircraft velocity will be different, because the calibrated or the calibrated airspeed will be much higher than the because the calibrated airspeed will be much lower than the truer airspeed. So this is the model for the calibrating the airspeed, and this is the Mach number equation, and this is the pressure. So that's all. Now we can jump into our model, which we, as we can see, this is our atmospheric model in the Simulink. So these are the two inputs of our model. One is the altitude, which is height in meters, and the true airspeed of the true airspeed with in meter per second, and these are the outputs of our model. One is the speed of the sound at that certain height, and the temperature with respect to that height, and the pressure and the density to that respective heights. This is the Mach number at which the aircraft is flying, and this is the calibrated airspeed. So this is our model, as we can see here. This is the input what we are giving. So these all are the, this is the small model what we have done through these equations, through this temperature and this pressure and density has been calculated through the perfect gas equation itself, and the sound speed of the sound is calculated by this equation. That's all. This is all of the output. As we can see, temperature, pressure and the density, these all are the three outputs of this small model. And in this model we are taking input of the Mach. In this model we are taking Mach number from the atmospheric model from here, and the pressure, so to calculate the calibrated airspeed, as we can see in this equation. This is the equation where we are inputting the Mach number and the pressure difference to calculate the calibrated airspeed. So this is our small model of air atmosphere, international standard atmosphere. So in the further days we are going to model the aircraft which we are going to simulate in this atmosphere. Thank you. So I will show you the small demonstration of our model in the sea level, which is the height of the zero, and we will take the true airspeed as a 150 meter per second, and we will run the model. As we can see at the hairs, as we can see from this our international standard atmosphere, at the sea level the airspeed was sound of the speed was 340, so it was a 340, and the pressure was 29 or 1 pascals. So this was it, and this was the 288 and this was the density, this is the Mach number, this is the calibrated airspeed. This is at the 0 degree because sea level, so the true airspeed of the aircraft airspeed and the calibrated airspeeds are equal. When we increase the altitude to 200 or 2000, which is like 2 kilometers, let's increase our true airspeed to the 200 meter per second. So as we can see from here, so the true airspeed of the airspeed is 200, but the calibrated airspeed is little bit much more lesser, and this is the Mach number 0.6, and this is the here of the speed of sound, this is the temperature, and this is the pressure, this is the density. So this is our small atmospheric model which we are going to use in our simulations of aircraft. So that's all.